Everyone, welcome back to Statics. So this time we're going to be talking about the moment of a couple. You're probably like, okay, is this a relationship course now? Are we going away from physics? No, this is not that kind of couple. It's kind of a weird name for it, but we'll see in a minute why it's called a couple moment. So what we're going to do this time is going to learn how to define what this strange couple is, what kind of relationship is it. And we're going to figure out some applications, why we want to do this. So let's get to it. So first off, you know that if you're turning your steering wheel, typically you put your hands on opposite sides of that steering wheel. You don't put both on one side. Sometimes you do, but most of the time it's on opposite side. 10 and 2 or 9 and 3, whatever. Well, there's a reason for that. There's a reason that you try to turn your steering wheel in that way. Now, when you're turning your steering wheel, typically you have the forces going in opposite directions. One hand pushes up, the other hand pushes down. If they both push in the same direction, it doesn't turn. If they push in the opposite direction, it turns. Now, the interesting thing about this is that we can then calculate the couple moment, the moment caused by your hands, in a simplified form. And this is what we're going to learn about today. This is actually called a couple moment. We have a couple of forces, which are the same in magnitude, opposite in direction, which are causing a moment about the same point, which in this case is the center. So, just like I said earlier, when you apply a moment to a steering wheel, it turns. Other things you need to realize is that the steering wheel itself does not try to move up or down or left or right. If you're turning it properly, it will just turn. It doesn't feel any forces pushing anywhere else. It doesn't really matter because the steering wheel is a lot stronger than you are. Well, the most of you probably. But either way, it's not going to move. So these are two things that matter. One, we have two forces in opposite direction. Two, we're going to learn about is that it doesn't cause any translation, only rotation. So a couple is defined as two parallel forces, parallel, with the same magnitude but opposite directions. And they're separated by some perpendicular distance d. That perpendicular distance is important. Remember, it's perpendicular, not angled, because there's infinite number of distances I could choose from if I choose just any angle I want. So only perpendicular. Now, when we have this situation, it's actually very simple to calculate. We just use our regular old force times distance. Now here's where most people get confused. You're like, wait a minute, there are two forces, it should be 2F times D. There we go, okay. You made a mistake there, that was a mistake. But that's not the case, that is actually wrong. Because I'm actually not turning, I'm not turning around this point right here, or this point right here. No, I'm turning around the center. So what I have here is, just like you might have thought, I have F, which is the right force of 1, times the distance, but over 2. Okay? The distance over 2, because I'm going halfway to that middle point where I apply this moment. And then I add that with the force times distance over 2. And what do I get? Well, I simply get force times distance. So that is why you don't see 2F here, or see D over 2 here. It's because I'm taking into account both. And I'm taking into account the fact that I'm only turning it around this midpoint. If I want to, I can also just use my regular vector analysis approach where I have the position vector and this force vector. Okay? Position vector and this force vector. But the position vector, once again, is from these two forces, where those two forces are applied. Okay? Where those two forces are applied. So, the cool thing about this is that a couple moment does not cause translation because the net force is 0. I have two forces opposite direction equal in magnitude. You add them together, they equal 0. So it does not try to make this move in any direction. All it does is try to make it turn. The second thing is that a couple moment is what is known as a free vector. So technically, I can move it anywhere I want on the same body. If I apply a couple moment to something, I can act like it applies anywhere. So these two, moment 1 and moment 2, you can see that they're not applied to the same point. With forces, we have to take into account a bunch of crazy stuff sometimes. But in this case, I don't really have to worry about it. I can just act like they apply at the same point and add them together. It makes it a lot easier on yourself. And this is one of those things that you're going to forget. You're going to get to your homework, so you're going to get stuck. And this concept right here, this is the super important concept, okay? So don't forget that couples are free vectors. You can move them around. Not just any moment, but couple moments are free vectors, and you can move them around anywhere you want. And with that, it makes the problems a lot simpler. So remember that. Okay. So next time, we're going to jump into an example actually doing this. We're going to do the scalar approach first, and then we'll do the vector approach. But for now, this is it. So remember, couple moment, two forces, opposite directions, equal in magnitude, with some perpendicular distance in between. Second, they're free vectors. You can add them together no matter where they're applied, as if they were at the same point. So with that, I'll see you all next time as we try out some examples. Have a good day. Bye-bye.